Hello students, welcome back to our course Environmental Modeling and Simulation, and today we will continue our discussion on Gaussian Plume models. We will see two different ways of applying the Gaussian Plume model in today's lecture, and I want to start this lecture by reminding all of us the reason why we use Gaussian Plume model. The most practical reason is because we want to give industries a way, a method to figure out what should be the minimum height of their chimney to ensure the safety of people living on the ground, the animals living on the ground. Now, the other application of Gaussian Plume model, which is also important, is to find out that if we know the emission rate for a particular chimney, and we know the height of the chimney, and we know the meteorological conditions that give us information on sigma y, sigma z, and can we find out what will be the worst case scenario concentration on the ground level? Basically, what will be the maximum concentration at the ground level when z is equal to 0? So today we are going to answer these questions, how we can use the Gaussian Plume model that we have to answer these two questions. So let's get started. So the first question we are going to answer is, what is going to be the worst case concentration on the ground level? So we want to find out the maximum concentration at the ground level. And we are going to assume that all other assumptions of Gaussian Plume model are relevant. So maximum concentration of ground at the ground level. So let's look at the chimney. Sorry. So this is our chimney, this is the effective height, this is the center line, and that's the plume right there. So there are some assumptions that we have made, and notice that whenever those assumptions are not met, we cannot use the model. So if the wind speed is very low, the model will fail, and I mentioned again in detail why it will fail in the previous lecture. Another thing to notice that when the wind speed is very low or when there is no wind, the diffusivity constants are not constants. The diffusivity coefficients dx, dy, dz, they are not constant. So we need to also not make that assumption. Another thing is that we are assuming there is no obstruction, which will not be the case in case of presence of obstructions like high-rise buildings, trees, forest, hills. We are also assuming that the wind velocity is constant, which means not only wind speed but wind direction is also constant, which is rarely the case. It's typically the case for very short periods of time. Otherwise, the wind velocity is quite dynamic. It will definitely not be constant at all for any period of time in hilly areas. So again, in hilly areas, we cannot use this model. We can only use this model in flat areas, and remember, since the wind will be constant, velocity of the wind will be constant for very short duration in flat, completely flat obstruction free areas. This model is only relevant for industrial estates this model is only relevant for industrial estates in flat areas, and also the short period of time condition is important. Okay, so we want to find maximum concentration at ground level. I mentioned this is a Gaussian Plume model, which means if you're defining such that our x-axis is in this direction, y in this direction, and z in this direction, then the maximum concentration in y is at the center line. The maximum concentration at z is also at the center line, right? Because this is Gaussian distribution, Gaussian plume. So if we want to find out the maximum concentration at the ground level, so we are in, let's say here is the place where we get maximum concentration. What we want to do is we want to find out the x that corresponds to it. So x is what we are trying to find. What will be the y and z? The z, the height of this location, because we are finding at ground level, is going to be 0. Right away we know this. What will be the y? Now since along the y-axis the concentration is maximum when y is equal to 0, we know that at the point, at the spot where the concentration will be worst, will be highest of the contaminant, will be the point where y is equal to 0. So we are going to put z equal to 0 and y equal to 0 in our equation, and we are going to get a much simplified equation which looks like this. So remember, this is x, this is y, and this is z, and y and z are 0. That's it. the part of the equation which is y square by 2 sigma y square will become 0. So, the exponential of 0 will be 1. So, that part then goes into unity. So, this is the equation we have, and now we want to find out when does C get maximum. Now, let us suppose, why do I believe that there will be a situation where the C will be maximum? And the reason for that is because let us look at this system. As x increases, x is the distance in the downwind direction, as x increases, sigma y and sigma z, they change, they vary with x. What happens is that as x increases, both sigma y and sigma z will increase. Which means if we look at our model that we have right now, we have two terms here, two factors. This is factor 1 and this is factor 2. So, as x increases, sigma y, sigma z is increasing, which means the denominator of factor 1 is increasing. So, factor 1 is decreasing. As x is increasing, in the factor 2, the denominator of negative exponential is increasing, which means the whole factor 2 is rapidly increasing. And now in our model, these two terms are multiplied to each other. So, one term is going down, is reducing as x increases, the other term is increasing as x increases. So, there will be a point where we'll have maximum concentration. Now, that is what we want to find out. To find out maximum concentration, we are going to use some analytical methods from basic calculus. Remember, to find the maxima, there should be two conditions that should be met. First is that the first derivative should be 0. So, basically in this scenario, dc by dx should be 0 at the place of maximum concentration, and then the double derivative should be negative. We will see we do not need to go to the double derivative because there is no local minima, there is only local maxima that we are looking at. Okay, so we need to derive this equation with respect to x. So, let us go ahead and let us do that. So, to derive that, we need to bring x back in the equation because we are deriving it with respect to x. So, sigma y, sigma z both have x in it. Now, in certain cases, especially when the atmosphere is either moderately unstable or nearly neutral. So, please note this down. When the atmospheric conditions, and towards the end of the lecture I will explain more what these are, but I will tell you briefly what this means. When atmospheric stability is either moderately unstable or nearly neutral. Now, what is moderately unstable and nearly neutral talking about? In one of the previous lectures on Gaussian Plume Model, I talked about dry adiabatic lapse rate, wet adiabatic lapse rate and environmental lapse rate. Environmental lapse rate is the rate at which the temperature of the atmosphere changes with height. Adiabatic lapse rate is the rate at which the temperature of the parcel of smoke that has been emitted changes with height, and that parcel of smoke is undergoing adiabatic expansion or not. So, it is moving adiabatically, it is not exchanging heat from its environment. So, adiabatic lapse rate and environmental lapse rate are not typically same. When they are same, they are nearly neutral. We have nearly neutral situation, nearly neutral conditions, which is here. When the environment cools down much faster than the smoke parcel cools down, the smoke parcel will rapidly rise up. So, we will see lot of vertical mixing of the smoke because the environment is cooling as the atmosphere, as we increase the altitude, as we increase the height, the atmosphere is cooling down very rapidly. But the smoke is cooling down according to its adiabatic lapse rate, which is lower than that of environment. Then the smoke will get increasingly warmer compared to the environment. So, it will rise faster and faster and faster. So, in this case we get unstable conditions. So, unstable conditions from pollution perspective are very important because we want vertical dispersion to happen, because the more vertical dispersion we see, the lesser concentration of the contaminant will be. The trouble happens when we have stable situation. When the environment is stable, the smoke parcel cools down faster than the atmosphere. So, as the smoke parcel rises, it is cooling down, but the atmosphere is cooling down much faster. So, it loses thermal buoyancy. Remember, we talked about thermal buoyancy, and we saw how thermal buoyancy can also be is actually dependent upon how hot the smoke parcel is compared to the ambient air. So in this case, we have stable environment, vertical dispersion is very less, vertical mixing is very less. So what we get is more concentration of the contaminant near the surface of earth or near the center line. Now under these two atmospheric conditions where we have moderately unstable scenario, so there is some vertical dispersion happening, but it's not very dramatic, because remember, when we were deriving the Gaussian plume model, we said that in vertical, in z direction, diffusion is important, dispersion is not so important. Sorry, diffusion is important, bulk action is not important. But if we are having very unstable environment, that not only the diffusion becomes complicated in the z direction, but due to the momentum of the smoke itself, which it is gaining as it rises up, we might have some bulk action also happening. So what we are going to do now, we are going to find out dC by dx, and we are going to find out the maximum concentration on the ground will only be relevant under these two atmospheric conditions. Typically, we teach about atmospheric stability in our first year in our college here, and in other colleges, especially civil engineering and chemical engineering students are frequently taught about atmospheric stability. But don't worry if you were not taught about it, because I'll go little bit more in detail towards the end of this lecture or the beginning of the other. Okay, let's come back to our dC by dx calculation. We know that sigma y, sigma z have x in them. Now we are going to write sigma y, instead of sigma y, sigma z, we are going to write what they are, what they represent, so that we get the x and we can derive this equation with respect to x. Now the reason I talked about atmospheric stability is because under moderately unstable environment and under neutral environment, sigma y, sigma z, they have a ratio. So the ratio, let's say, is sigma y to sigma z is equal to k. Let me write it up so that we keep this as a record. So under these scenarios, sigma y by sigma z is equal to some constant k. Yeah, and what we are going to do is we are going to replace sigma y with k here. So we are going to get c is equal to q by u. Let's do one thing. Let's define a different k just to make life a little easier. Let's say sigma y is equal to capital K sigma z. So now we have capital K sigma z square. So we get rid of the square root in sigma z minus h square by 2 sigma z square. So now we can substitute the actual value of sigma z, and what we will get is this. C is equal to q by 2 pi k dz is your diffusion coefficient in the z direction, vertical direction, which will not be the case when u is very small. I also need to remember to put u here. Oh, the u will get cancelled. X square okay, now we have x in the equation. Now we can differentiate with respect to x. To make this derivative slightly easy, let's define two new constants. Let's say that this part is equal to a. So a is equal to q by 2 pi capital K dz, which is diffusion coefficient in z direction. And let's say this part is equal to b. So we capital B. So we are defining capital B as h square u by 4 dz. So now what we have is, so this has been defined as capital B. So now we have simplified this equation. We have very simple equation here. C is equal to A by x square. Very easy to differentiate, you will see. E to the power minus B by x. Okay. Now we are going to differentiate this. So dC by dx, we can differentiate in parts. Differentiate first part, keep the other constant plus, then repeat on the other side, and we get there. This is what we get. So now for finding out the maxima, the x where the concentration is maximum, two conditions remember, dC by dx should be equal to 0. Now this is a condition for both local minima and local maxima. We will see that this is only going to be the case when, for one situation, dc by dx is only going to be 0 when this becomes 0. This is not going to be 0 unless x becomes very big. Actually this so no, so this is not going to be equal to 0, but this will be equal to 0 when b by x minus 1 is equal to 0, which means b is equal to x. Now we have figured out that dc by dx is equal to 0 when b is equal to x only in one scenario. We have only one fixed point for this, and we know that that fixed point is going to be a maxima. You can actually draw the phase portrait and look at it. Now since we already know it's going to be a maxima, because we already saw that this term decreases as x increases, not here, not this term, sorry. We already saw that this term decreases as x increases, this term increases as x increases. So what we are going to get is a case of maxima. So we know that this is going to be maximum concentration. So b is equal to x. Now what was our b? B was equal to h square u by 4 dz. So b is equal to x is equal to h square u by 4 dz, right? So let's replace sigma z in this. Let's put sigma z back. What you will get is 2x dz by u. So we want to put sigma z back is equal to h square by 2. So we get sigma z square is equal to h square by 2. Square rooting on both sides. Sigma z unit is meters, by the way, and it's never going to be negative. Same thing with the height, we are not going to get a negative height. So we are going to get this. So when sigma z is equal to h by root 2, or when x is equal to h square u by 4 dz, if you know dz value, dz value, diffusion coefficient in the z direction, this is where the maximum concentration is. Now what we can do is we can substitute the sigma z value in our equation here. So we know that sigma z is equal to h by root 2. So we can take this system or this system and replace sigma z for h by root 2, and we can find the maximum concentration. So not only do we know where the concentration is going to be maximum, under what conditions, but we can also find out the maximum concentration. So let's do that now. Okay, so when we put this value of sigma z in our original equation, the concentration, the maximum concentration C max at this x for this value of sigma z comes out to be q by e pi u sigma y sigma z. This is what we get. And remember the assumptions we made, right? We made that the atmosphere is either nearly neutral or moderately unstable. So if it's a stable environment, this won't work. If it is very unstable, this won't work. Only for two kinds of atmospheric stability, this system will work. Also, all other assumptions that we made in Gaussian Plume model are also true. So wind can't be too slow. This is only valid for short durations of time and in flat terrain, because the wind velocity will change over time. Okay, so we have found the sigma max, and we have found the maximum, the location where C max, sorry, not sigma max, C max. We have found the location where the concentration will be max, and we have also found the relevant sigma z value. The next thing we can do is we can calculate the required stack height. So for example, if I know that the permissible level of a particular contaminant, so let's say some industry is releasing some amount of lead in their from their stack, there is some mercury based compound that is being emitted in their smoke. So if I know the maximum level of mercury that is permissible at the ground level for human exposure, so I know the C max permissible, can I find out what should be the minimum height of the chimney? What should be the minimum height of the stack? This is very important question. This is where regulations come in. Yes, we can. So let's do this. We are going to use what we have here. So now we know that C max is going to be this much. So what we are going to do is we are going to take the C max, which is our permissible maximum concentration of the contaminant. So let's just call it C STD for C standards, and we are going to replace this here. So we get C STD C standards is equal to Q e pi u sigma y sigma z. We know the Q for given wind velocity, we know C STD, so we can get an idea of what the sigma y and sigma z should be. So let's do that. So minimum stack height for permissible level C standard. So C standard will be equal to C max, which is equal to Q by E pi U sigma y sigma z. Now we also know that sigma y is actually equal to root 2 dy x by u, and sigma z is equal to root 2 dz by u x. So we know this, so we are going to replace these here. And what we are going to get is, since this is a product of sigma y sigma z, the product of sigma y sigma z will be product of these two. So what we are going to get is 2 will come out, root 2 square root of dy dz, u will also come out, and then we will have x here. So this is basically 2x u by root dy dz, and this is what we are going to replace here. So what we get is C standard is equal to Q e pi u into 2x by u root dy dz. U and u will cancel each other, and so let's take x here and C standard here. Yeah, so we are taking x to the LHS and C standard to RHS because we know C standard. So x is equal to Q by u has gone, root 2 dy dz, right. So this is where the maximum concentration will be. So now we have found what will be the location where the maximum concentration of the contaminant will be, and the maximum concentration is the permissible, the quality, air quality standard. Okay. Now if you want, you can again write this in terms of sigma y sigma z. So you can be like x, then you will get xy is equal to sigma y sigma z u by root 2 dy dz. Okay. So we have found the x for which we will have maximum concentration, which is C standard. Now we need to find the height of the stack. So how do you go about that? So now we have to find the height, because the question was find the minimum stack height. We have found the x, very good. We know what C max should be. Now for finding the height, we need to go back to our derivatives. We need to look at this. We know that for maximum concentration, sigma z will be equal to h root 2. So now we have sigma z here. So sigma z is going to be h root 2. So let's replace this. If you substitute, let's say here we are. So we have C standard is equal to Q by E pi u sigma y sigma z. For maximum concentration, sigma z is going to be equal to h by root 2. So we write C standard is equal to Q by E pi u sigma y h by root 2. This is how you are going to find out the value of h for which, the minimum value of h that you need to make sure that the safety is maintained, people are safe. Okay, so these are the two applications of the Gaussian Plume model. The first one is to find out the maximum concentration at the ground level, and then the second one is to find out the minimum stack height. Now I want to discuss what I promised you I will discuss about atmospheric stabilities and give you some visual ideas of how the atmospheric lapse rate, how the environmental lapse rate or atmospheric lapse rate and the adiabatic lapse rate together determine the vertical dispersion, the movement, the vertical mixing of the plume and atmospheric stability. I am not going to go in detail, but just very briefly. This is not part of the modeling, but this is very important if you want to understand how contaminants move through the environment, and in case the situation is not what the Gaussian Plume model requires, you should be able to adapt, you should be able to modify. For that you need to understand the basics. So let's say on y-axis we have z, which is altitude, right? And on x-axis we have temperature. Okay. So as the smoke rises, it's going to lose temperature. So let's say this is the smoke temperature, T smoke. As it rises up, it's going to lose heat, it's going to cool down. The typical for a dry packet of smoke, a dry parcel of smoke, dry adiabatic lapse rate. Now again there are two assumptions here. First is that the smoke is dry, it does not have any moisture, which may or may not be the case. For example, steam engines, they were releasing steam along with other contaminants. And if you have steam coming out, if you have combustion, one of the combustion product is moisture, then you will have to use either wet adiabatic lapse rate, or you'll have to figure out what your adiabatic lapse rate is. The second assumption is that the smoke parcel, as it is rising up in the atmosphere because of thermal buoyancy, it is undergoing, it's an adiabatic process. If it is not an adiabatic process, then again this will not be valid. So the typical dry adiabatic lapse rate is losing 1 degree Celsius per 100 meter rise. So for every, this is, let's call it, right, for every 100 meter that the smoke parcel rises, it loses 1 degree Celsius heat temperature. Now let's look at our environment. So let's say the environmental temperature here, where the emission happened, so Z of emission, so it could be the center line of your smoke chimney, could be the ground. So air here was this temperature, and the air also loses temperature as we go up. Things are cooler, air is cooler as we rise up, at least up to a certain atmospheric level. So it will also cool down. Now it can cool down, okay, need to repeat this part. The rate at which the atmosphere loses temperature as we rise up is known as atmospheric lapse rate. I've heard people call it environmental lapse rate too. Lapse because the temperature is going down. Atmospheric lapse rate, again, it depends upon many things. It depends upon the insolation, which is incoming solar radiation. It depends upon terrestrial irradiation, which is the heat emitted by the land. It depends upon the wind. It depends upon meteorology in general. So atmospheric lapse rate is something that we ideally know from our meteorological data, and it will not be constant. It's changing per every day, from time to time, okay, from season to season, place to place. Dry adiabatic lapse rate is roughly constant. Dry adiabatic lapse rate, which is loss of 1 degree Celsius per 100 meter. So the environmental lapse rate or the atmospheric lapse rate might be same as the dry adiabatic lapse rate, which is losing 1 degree Celsius per 100 meter. This is the case. So what will happen is, as the smoke rises, the del T, the differential in the temperature, will remain same. So the thermal buoyancy will remain the same, so the smoke will rise normally. Such an environment is known as neutral environment. Now let's look at another scenario. I'm going to only teach you some basic scenarios. I'm not going to go in detail because this is not air pollution class. The other possibility is that the environment cools down much faster than the smoke. So basically the atmospheric lapse rate, ALR, is lesser, because they are negative, is lesser than the dry adiabatic lapse rate. So maybe instead of 1 degree Celsius per 100 meter, it's losing 2 degrees Celsius per 100 meter for some reason. Now in this scenario, what is happening is that the thermal buoyancy, which is proportional to some difference between the temperatures, it could be T4, T2 or just del T, the thermal buoyancy of the smoke is increasing as it rises up. So what will happen is that thermal momentum of the smoke will increase as it goes up. Vertical dispersion will be very nice. So we'll have the smoke that is rising up will shoot up, will run up. And it will run so fast up that the air here at the top will get compressed and push it back down. So this is where we see that the smoke parcel, the plume looks like this. It moves up and down. This is called looping. So this is an unstable scenario. Unstable. Now let's look at the third scenario that I'm going to talk about. which is when the environment is not cooling as fast as the smoke is. So, environmental lapse rate or atmospheric lapse rate is, let's say, minus 0.8 degree per 100 meter, whereas the dry adiabatic lapse rate is 1 degree per 100 meter. So, what's happening is that the thermal buoyancy is getting down. As the smoke rises, it notices that it is not as warm as compared to the air around it. So, its tendency to rise up and mix vertically goes down. So, in this case, we call it a stable environment. So, vertical dispersion is low. From human perspective, animal perspective, well, humans are also animals, but from perspective of environment and contamination, stable environments are not good for us because they prevent vertical mixing of our contaminants. Now, there are other kind of atmospheric conditions. For example, when we get inversion. So, inversion is when the air becomes warmer than the smoke, and then we know that the smoke will not rise above this. The smoke is trapped at this height. This is known as mixing height, mixing depth. I'm not going to talk more in detail about it, but you need to understand that what atmospheric stability is, and I wanted to cover it. All right, students, this is all for today. In the next lecture, we will talk about groundwater and how we can use the concepts you have studied in air for groundwater modeling, and how groundwater modeling will have different boundary conditions and different scenarios. As I mentioned, it will have retardation, and depending upon the kind of contaminant, it might degrade. Thank you.